There we go. All right. So databases then. I must apologize for this unspeakable cruelty, but we do actually have new material to cover today.
A lot. Final class on Friday, and you have new material to cover, and you know what you're doing.
And a test?
And an exam, yes.
Oh. Kevin?
Yeah, Kevin Brown.
Yeah.
So what is on the final exam for you?
Everything.
Everything. Everything. Memorize all this one.
Everything the flowers.
He was not specific.
When we say everything, it's everything. All. For this stuff? Okay. I'll do up. I thought you were talking about UI. Oh yeah, you're right. No, I don't know.
So for this class, definitely after the midterm. Yeah. The exam is not cumulative of the whole class.
Wait, it's not, but I mean, it's surely gonna ask us to write, like, select stuff inside other things. No, really?
You don't have to write any select queries on the exam.
We have to
That's
write like,
really shocking. Okay,
Yeah.
fair enough.
I know, it's a little shocking, right?
we have to write T-SQL,
Um,
like the cursors and the
Yeah.
begin.
so, camera running? Camera is running.
Want me to push it over?
No, it's okay. So, I think I've already said this, so. You know how last time there was like a bunch of multiple choice and then write some select queries?
Yeah.
This time there's a bunch of multiple choice and do an ERD.
I'm shocked. Okay.
Yeah,
That's
So-
actually, that's not nearly as scary as I thought it was gonna be.
Yeah.
Okay. Whew.
so, okay,
Okay, just getting on the station.
okay, yes,
And the multiple choice part is gonna be also every topic after midterm, right?
yes.
Okay.
It's not cumulative, so we are 100,000% focusing on the material that's been covered since the midterm. Yes,
That's to say that like everything, the only thing that's not multiple choice is going to be the ERD or,
yes,
okay.
yeah,
You just removed like 15 kilograms from my bag.
alright. This is not designed to be the course that kills you.
So there are many courses that are not designed to kill us, but
I'll be changing this at my earliest opportunity, but fortunately you guys are one of the semesters before I fix this course.
Like Indiana Jones sliding under the slowly closing stuff.
Yeah. No, actually, like, what I want to do with this course, right, I want to take a lot of the fluff, which is like basically most of the stuff that's been covered since the midterm, and I want to replace it with fun stuff. Like, how do you actually, like, do, like, containerized databases and get them connected, and, like, how do you do servers, or how do you do databases, and, like, you know, maybe we even have some time for some Mongo.
Awesome.
We-
Please get them writing select queries sooner rather than like
Oh,
a
yeah.
month and a half into
Oh.
the course.
Oh, bloody hell, like, we gotta ditch this GUI nonsense. Like, it's gotta be command line interface for everything.
For a class called database theory, there's very little how do we do databases.
It's strange. It's just, like, one of my observations of this course is that it kind of reads off two different sheets of music. Like, the first end of it is like, oh, we're not actually gonna require you to create tables. Right? Like, if you'll notice, we never actually tested you on a create table statement.
Super anxious about that showing up on the exam.
Yeah.
We never did it.
Yeah, and like the theory, the reason for that, so I've been told, is because this is not something you'll be expected to do in industry. Because database experts set up databases. So I ask you a question. Why did we spend the last month of this class normalizing databases?
To create databases.
Yeah.
Right?
Pointless. Tables.
I mean, it's not pointless because it's on the exam.
I guess maybe if we wanted to join like a startup and we're just like the only IT guy, maybe
Yeah.
then we create a database.
See, this is the feeling that I kind of have. It's like, even if it's a rarely used skill, it's still important for it to be in there. Like, basically, like, what I would take it as like more comprehensive coverage of the stuff that's important, and then like knocking out some of the things, like maybe even TSQL itself.
Yeah, I mean, we did cover normalization, but we only covered like the first half of it, so.
Yeah.
I've-
All right.
I've never really understood like the whole thing of covering all phases of normalization. To me, it kind of feels like there's several phases of normalization, right? But it's not like, okay, you can use this phase for something, but this phase has a different purpose and this phase has a different purpose. It just feels like wrong, 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 and then right.
Yeah.
I've never really understood why we don't instead just learn how to take it and then just make it right.
So basically, like, the answer to that question is like, unless you follow all of the steps of like long division, how do you know your answer is right? It's like one of those types of situations, right? So like, how do you know that your third normal form is correct? You started with a correct second normal form, and you applied third normal form correctly. So like, that's the reason. It's been observed to me by other people in the class that it's actually quite, it's an easy mental mistake to make to skip over second normal form and jump straight into third, right? If you think about like a common sense, like if you're thinking it through with common sense, it's quite easy to do that because, you know, second and third normal form are basically the same thing applied to two slightly different types of data.
Yeah,
But,
second is like attack on rows, and then you got like customer ID, name, address, and you think, okay, I can just turn that to its own table, but oh, that's on third normally, you can't do that in second.
See, I kind of disagree with the way that it was taught on the first time around that we did it, where it was like attack on columns, attack on rows, and then, right? Attack on more rows? That's, I think, like, the thing that we should have started with was the analysis that we ended up doing with the arrow notation.
Yeah.
Right? It's like, first normal form is just get it out there, right? Remove calculated columns. Find your keys.
Yeah.
Second, stuff that correlates to the keys. Third, things that correlate to the stuff that's not the keys. That's like, as mental steps, that's actually much easier to remember than like sure, attack on rows, attack on columns sounds good, but it doesn't imply the operation. How does one attack the rows? How does one attack the columns? Right? Whereas, you know, find the things dependent on the primary key is both a thing that's fairly easy to remember and the functional description of what you actually do. So it's, I think if you're gonna memorize how to do normalization, memorize that one. But I should do these slides. All right.
Before you get into it, can you make them available on my campus?
Oh, yeah, that's a good idea. My most humble apologies. I hate my Canvas. I hate my Canvas so much, almost as much as Microsoft. And that's saying something. So, lecture 12. That's the wrong hotkey. Which one is it? Not that one. And not that one. There we go. Found the hotkey. All right. Transactions and concurrency control. So, the same information, but in bullet points. So, let us consider a scenario. Let's say that you are a student and you are wanting to buy a hoodie at the campus store. If we consider the form the database will take at the campus store, it's very, like, you know, third normal form, everything's done into separate tables, right? We might touch 3 tables in the course of this operation. The student table, which holds your account balance, right? And we have the very, very, very exceptionally clever student name, Stu Dent. A product inventory table where the hoodie is stored, and an account number which is presumably the money that's presumably where the money is going to be dumped into, right? So, in order to purchase a hoodie, we have to touch all 3 of these tables. How many SQL commands do we need to do that?
3 updates.
3 updates. Right. 3 updates. This is a somewhat simplified version of the updates. This is problematic. All right? The reason this is problematic, let's say we're on this one. All right? We execute this one. Okay, this is the one where the student's balance is deducted. All right? We execute the next one. Inventory is reduced. Presumably there's a rule that we can't reduce the inventory past 0, right? So if we've run out of inventory, we can't sell the product. Now let me ask you a question. Let's say we had 2 students, right? Student A and student B. Let's have a timeline of transactions from these 2 that are being executed, all right? So let's say student A executes, I hate this room. Although it is kind of nice to be able to draw on the slides, I just one in the middle, please. Let's say that student A executes statement 1. Okay. Let's say that next, student B executes statement 1. Okay. Let's say that next, student A executes statement 2. Now, let's assume that as the result of the execution of statement B, we no longer have any inventory of this item. Right? Student A gets the last hoodie. What happens when student B attempts to update the inventory table to reflect the purchase of the hoodie?
They don't get the hoodie, but also their money's gone.
They don't get the hoodie, but their money's gone. This fails. This one went through, but this one failed. So the student's account has been deducted the money, but they don't get the hoodie. Right? Now, this works better if you think of it as an online store, right? Like, in person, there's one cash register, and, you know, if a cashier was interrupting one transaction to do another one, the manager would probably intervene. Yes?
I also don't think you would try to buy a hoodie that's out of stock in person.
Yes, exactly. Like, that you have to actually walk up to the counter with the thing you want to buy, so.
No, we don't have it.
Yeah, exactly. But on an online store, you can see how this would happen, right? So how do we solve this problem? Basically, we take these three operations and we say, this is a block of transactions. Well, actually, we call this we call the block itself a transaction. It's a block of statements which together form a transaction. We say, these things must not be interrupted, right? This sequence of statements must be permitted to execute in its totality, or else the whole update should be thrown away, right? And this makes sense. Even if we take a scenario where we're just talking about A, or let's throw out A, let's just look at B, right? Let's say we execute 1, we execute 2, and then 1 fails. Or we execute 2 and it fails. 1 has still been executed, right? The account has still had the money removed. What do we do now? We spin up another SQL statement that puts the money back, right? That sounds messy. No, we say, unless all 3 of these execute without fail, none of them should be considered to have applied, right? This is the purpose of a transaction, okay? So, this is a procedure which performs these changes. You can see that in this procedure, we have our 3 updates which occur. We're basically guarding this with an if statement. We check before we execute the updates if the transaction can be performed, and then we, basically this is the proactive solution. We check ahead of time with an if statement to see if the things can be updated, and then and only then we update them.
So is it kind of like, in a way, it's kind of like a try-catch almost?
A little bit, yeah, but there's a problem with this one. Under a concurrency scenario, we haven't actually fixed the problem, right? A procedure in a multi-threaded environment, multiple procedures can run at the same time, right? But this is like, we're starting to think about this as a block, right? So, yes. So, definition of a transaction. A logical unit of work that must be completed in its entirety or be aborted. A transaction is created every time you read from or write to a database. So each individual SQL statement is itself a transaction. But we want to be able to collect them up into larger transactions, right? Many transactions consist of 2 or more database requests. A transaction that changes the content of a database must alter the database from one consistent state to another. So when we, in this scenario, where person B is charged the money but not given the item, this is what we would consider an inconsistent state. The state is not, it's inconsistent. It's not consistent with how a transaction is supposed to occur. There's a problem. We want problems to not happen, right? So, a consistent database state is one in which all integrity constraints are satisfied. Yes. All transactions must adhere to another fun acronym, ACID. Hopefully this is not dissolving your attention. Was that question, was that joke a little basic?
Oh, man, you don't.
People don't do drugs anymore.
No, that's true, yeah. All right, so, atomicity, consistency, isolation, and durability. Atomicity is the most important one and probably implies all the rest of them, actually. So, all right, I have a question for you. What is an atom? Science question.
Tiny particle that makes up everything in the universe.
A tiny particle that makes up everything in the universe except the things it doesn't make up. Yep.
Quarks. I don't know, made up quarks and gluons.
Yes. So, all right. A little bit of a lesson in ancient Greek for you.
Okay, makes all the matter in the universe, there we go.
Yes, there we go. So in ancient Greek philosophy, the ancient Greeks were pretty amazing. They actually had, they had a philosophical theory which, actually is the way that science turned out. And that was the theory that everything, all matter was made of, very, very small particles, and that those particles are fundamentally indivisible, right? This was one of the ancient Greek theories. There were, of course, ancient Greeks, there were many competing theories about things, right? Possibly they thought that, these indivisible particles were ultimately one of the four elements, or something like that, right? But, they had that idea of the tiny, tiny indivisible element, right? That was called the atom, right? Now, modern science comes along, and people are like, ooh, molecules. Alchemists come along and they're like, ooh, matter changes when you subject it to things. This is interesting. Maybe we can turn it into gold. Turns out, no, you can't turn it into gold. But they didn't stop them trying. And they did, a lot of very interesting stuff arises there. The first isolation of oxygen and hydrogen. Do you know why hydrogen is called hydrogen? Because, they were able to do an early form of electrolysis, and it was the thing that was born from water. Right? Hydrogen, yes. So, but molecules weren't it, right? We had to go a little deeper. We found the atom. That must be it, right? That's the smallest thing. We found the smallest thing, guys. Let's call it the atom. And then it's these atoms have some interesting properties. Some of them seem to have things inside them that are smaller than atoms. What do we call that, guys? I guess we call them subatomic, because it's under the point of the indivisible thing we thought that was indivisible. So, nice work, physicists. Also, nice work on getting electric current backwards. You guys know that one? Electric current is actually the opposite, when current flows, it's actually the opposite way that the electrons are flowing. So technically with respect to current, it's flowing backwards all the time because the actual particles are going the other way. If I say I have 5 amps of current this way, I have 5 amps of electrons going that way. So good work on that one too, physicists. But who could have who knew that electrons were negatively charged, right? It's an arbitrary decision what's negative and positive anyway. But anyway, so atoms. The idea of indivisibility. We have a much better implementation of atomicity in SQL transactions than we do in matter. In matter, atoms are not indivisible, but if we are applying atomic transactions, it means they are whole and complete and they execute all completely or not at all. Atomic. Alright? Make sense? So far so good? Alright. Either the effects of all or none of its operations remain when a transaction is complete. They are either committed or aborted. In other words, to the outside world, a committed transaction appears to be indivisible or atomic. A transaction is a unit of work that appears as if it is performed. That is literally the same thing written 3 times. Okay, thanks, the slide. Alright, so, how does this apply to our previous scenario? Our 3 tables must be updated, all 3 of them, or none of them. The problem that we experienced here between updates 1 and 2, we would have the same problem between 2 and 3, right? But, so we have to do them all at once or not at all. Every transaction, so this is consistency. Every transaction must leave the database in a consistent state, i.e. maintain the predetermined integrity rules of the database. All constraints must be satisfied with each update. A transaction must transform the database from one, this is again like the same thing said twice. So here's the way to think about the consistency angle, all right? When it has to do with the selection of the statements that we put in the transaction. Don't split a transaction in 2 when you're designing them, right? If you did operation 1 and 2 as one transaction and then 3 as another, that's a violation of consistency. After the execution of transaction 1, you would be in an inconsistent state until you executed the second transaction. Therefore, those should be all one transaction. This is not that difficult logically, as with a lot of material in this course, you can kind of common sense your way around pretty well, right? There's no reason to split up a set of a logically consistent set of transactions into multiple sub-transactions, so don't, right? But yeah, so that's consistency. So isolation. Transactions may not interfere with one another, even in a multi-threaded parallelized database. This is the tricky part. If you want a good course on parallelization, take the one that Dave Gilbert offers. It's a good course. He likes it because he says, I must have a scary reputation or something because I only get good students in that class. But parallelization is also a difficult topic, but very useful. The effects of an incomplete transaction are not visible to another transaction. A lock guarantees exclusive use of a data item to the current transaction. Providing isolation is the main goal of concurrency control, the second half of this. Yes?
Basically it says transaction should be independent of other transactions, right?
It's not quite. You have to think of it in these terms, all right? Resource management, all right? A table is a resource in the same way that for a CPU, a file is a resource, right? Does the operating system, let multiple processes write to the same file at the same time? No. Right. If one process has a file open for writing, another has to wait until it's closed it to then open it for writing. Right? That's basically like the whole second half of this talk. We'll get there, right? We'll get there. Just put a pin in it, we'll get there.
Hopefully, I don't put a pin on it.
Durability. Effects of successful committed transactions must persist through crashes or system failure, typically by recording the transaction's effects and its commit events in a non-volatile disk memory. So basically, when you're finished a transaction, even if the sub-transactions are being stored in RAM, when you hit commit, that saves it to ROM. Alright? Possibly a couple of different ROMs. So, transaction management. The ANSI standard to govern database transactions is supported by the SQL commands begin transaction, commit, and rollback. So we have some new commands. It's 1 week till the test, but we have some new commands for you.
We're maybe on the test.
Yes, this is stuff is testable on the test.
Oh, yeah.
So begin transaction starts the transaction. Commit completes the transaction. Rollback aborts all changes, returning the database to its previous consistent state. So basically, you can kind of think of commit and rollback as being two sort of different forms of return statement, right? You've got one return for success, that's commit. You've got one return for failure, that's rollback. When you roll it back, you abort all changes. It goes back to the state it was in before you made any of these changes. Question?
Yeah, how does the script know it was a success or failure though?
You tell it,
Okay.
right? Transaction logs are used to keep track of all transactions that update the database in case of rollback, append, or system failure. I don't know what append means. Append? I don't know. So, consider the following transaction.
Mine is the unexpected failure of a piece of computer software. Don't know why I
Oh.
would just say that.
The
The unexpected failure of a piece of computer software.
is an append.
Yeah. I don't know why they couldn't just say that instead of using some obscure term. I've never heard that in my life.
I have been doing computers for I've been a programmer for 20 years. I was a nerdy kid who liked to use computers a lot when I was a kid. That's how I ended up where I am. I have never heard the word append before.
Also, I feel like system failure might cover that as well. So.
Yeah, this is some nonsense 70s term. I guarantee it.
Like abnormal end or something?
Yeah, ab-end. Yeah, that's it, probably. Abnormal ending. Ab-end, append. So dumb. Oh, okay, alright. Transaction. Print, begin transaction. Update. Sure. This is, again, community hospital database. We have a couple of select queries that show that we execute during the transaction, and then it immediately rolls it back so as to demonstrate what rollback means. That's what the purpose of this program is. Like, a transaction where you always roll back at the end is there's no point to it because it doesn't modify state. You can also optionally provide a transaction name. Is this screen flickering? Just a
Yeah.
little, right?
Yeah.
It's very annoying. Instead, you can commit the transaction at the end, and then if we ran this, you'd find that this matches that as opposed to matching that, which is what it would do if you had rolled it back. So this is just intended to demonstrate what committing and rolling back does. So do we have a version of that that does the, no, okay. You're not gonna show me the if statement? Alright. You're not gonna give us the working example, alright. So, you put an if statement in, you roll back if everything works, you don't. I guess like, if
Like
a
row count like gets returned and you know something was updated, could that be
Yeah.
one signal?
I'm going to assume that, although it's not stated in the slides, I'm going to assume that if a statement fails due to the violation of a constraint, that will automatically roll back all of the transactions. So, although, you know, you should, it would be nice if it said that. The coordination of simultaneous execution of transactions in a multiprocessing database system is concurrency processing. This is to ensure the serializability of transactions, execution of transactions in the correct sequence. Words, lots of word salad on that slide. Basically, we're going to talk about semaphores. The slides call them locks, but these are also sometimes called semaphores. We need to avoid data integrity and consistency problems, obviously. Lost updates, that's bad. One record simultaneously updated by two different users. So it's kind of impossible to understand what's going on unless you understand what a race condition is. You guys, I sometimes mention this in like various classes, but does anybody not know what I mean by the term race condition? Really? Everybody knows that?
So I kind of understand it, but I feel like you should probably say it. Just
Okay, I'll yeah, okay. So this is actually a simplified version of a race condition. Yeah.
They just do two things, try and access the same thing at the same time. It's literally a race to see who gets it.
Well, I mean, it's a race, but the last person wins,
Yeah.
right? So if we have person A and we have person B and we have some kind of shared resource, right? Sometimes this is a file, sometimes this is a table. Let's say that assume there's no control whatsoever on who gets what when. If person A opens something for editing, and then person B opens something for editing, right? Then person A writes their changes back, and then person B writes their changes back after person A, right? We get into a situation very quickly where the changes made to this file by A exist temporarily, but are immediately overwritten by the changes made by person B. So anything that A wrote is lost, right? Because we are in a computer, and when we write to something, it's not like we're writing on the next page in a ledger book, right? We are overwriting memory. So that's a race condition. It's a race where the last person over the finish line wins, right? So that's what we want to prevent. So how do we solve the problem? When person A opens the file gets locked. so that person B cannot open it until the lock has been released. Only at that point can they open it. But they will open it after they see A's changes. Right? Does that make sense? So, this is sometimes called a semaphore. Sometimes it's called a lock. Make sense? Obviously, in the case of database, like if this is a database table, right? You can get into all kinds of inconsistent states if you don't lock the file, right? Data can be lost. The thing you're retrieving can be inconsistent. You know, again, in this scenario, if somebody tries to read out of the database when we're halfway through one of these things, you might get a wrong inventory for the number of transactions that are supposed to have occurred, right? So we have to lock the things down while they're being modified. Yes.
Semaphore is pretty close to how you say traffic light in Spanish. Is there a relation there?
Yeah, it's like the same thing. Yeah, like yeah, like it doesn't surprise me at all that like the in Spanish a traffic light is called like a traffic semaphore because like I'm pretty sure that like railway signals, like when they look like this, they're called semaphores as well. In fact, have you ever seen flag semaphore?
Mm-hmm.
Not for another, not to pull us onto another tangent, but right? This is a language kind of a little bit similar to similar in some respects to
So they communicated to a JIT.
yes. This is similar to this is basically what Morse code replaced. But like if you go back to like your like I don't know, these ships sailing around the sea in like the 17th century, the way they would signal messages to each other is by holding some brightly colored flags in like different orientations to signal different letters. It's like we attack at dawn type thing. But yeah, this is, as far as I'm aware, this is like the earliest form of semaphore that I'm aware of historically. There are probably older examples of this, but yeah, this is used in like a military context, but particularly in a naval context. But yeah, although that doesn't really, basically, person A is using the operating system to signal that you are not permitted, and that's why it's called a semaphore. Let's see, where are we here? My wife's in the Navy. She had a naval communications officer test her Morse code at one point, and he said, yeah, you just need to be a little bit faster and you'd be up to the same speed as an AVCOM. So, locks and bagels. No! So the way that we guarantee the exclusivity of a data item is using a lock. Locks are released when the transaction is committed. There is a lock manager which manages the locks. It's a software process that you don't really need to know about except for the fact of its existence. You can lock whole databases, tables, pages, rows, and fields at individual levels. But we're going to talk about table because that's kind of the functional unit, right? So, boop, there we go. All right. That's going to be really loud. Sorry, YouTube guys. So, should put a headphones warning on the video, but I won't. So let's do a little thought experiment. let's imagine we're locking things at the level of tables. In this scenario, we had to update 3 tables. How many locks do we need? We need 3 locks. That's right. So how do you obtain 3 locks? This sounds like a trick question, but it isn't.
Long tail.
Something that said luck equal true or something like that.
Well, let me ask you a question. How do you eat 3 sandwiches?
One bite at a time.
One at a time,
Oh,
right?
that takes time, so you can buy
How
one.
big is the
Parents still
sandwich?
buy.
Asking different questions.
I mean, you put all of them in the stack and you buy it.
I mean, well, okay.
So I left them on $85.
I mean, it wasn't that bad an analogy. That was a pretty good analogy. Come on. So, the way that we establish locks is using a 2-phase protocol. All right? In general, if this is not that difficult to understand, all right? In phase 1, we get all the locks we need. In phase 2, we release all the locks we have. It's like the big violation of this protocol is for us to unlock something, lock another thing, unlock that, lock another thing, and then finish, right? We want to get everything we need up front and then release everything when we're done. All right? Why? Here's a question. Hypothetical scenario. Let's say, this diagram's going to get more complicated. Let's say we have person A. Let's say we have person B. Let's say we have 2 files that we need to communicate with. So, person A and person B both require both of these files to perform their transaction, right? File 1 and file 2. Let's say that the way the timeline goes, because you can only get 1 lock at a time, right? Let's say person A locks file 1. Let's say that next person B locks file 2. Let's say that person A now seeks the lock on file 2 and is denied. You can have it when it's released, right? You'll wait for it to be released, please, thank you. Person B says, I would like a lock on file 1, please. And the operating system's like, no, sorry, can't give you that until it's unlocked. What are we stuck in?
So deadlock.
That is the definition of a deadlock. Yeah. This is, like, you may have heard the term deadlock before. This is what it technically means. A's process cannot continue because it requires resources it doesn't have. Person B cannot complete their transaction because they require things A has. A needs B to release, B needs A to release. Neither one is releasing because both needs a lock on the other file to release. Does that make sense? So far so good? Did we just accidentally learn something? So that's what deadlock is. Basically, the more you're asking for locks and giving them back and asking for locks and giving them back, the more likely you are to end up in this scenario. But this is not sufficient protection against deadlocks. Deadlocks are very difficult to prevent entirely, right? what in practice happens most of the time is you do some reasonable things to try to prevent deadlock, such as the two-phase locking protocol, and then you have like a watchdog watching to see if things get stuck into a stuck state, and if they do, unstick them. Yeah.
So to fix this, would you have like 3 locks, one around file 1, one around file 2, and then another lock around both of them, and then allow one person to get through that at the same time?
In theory, that is not a bad idea, right? You could extrapolate that idea to, well, maybe the problem is fundamentally that we're asking for these two things individually. If there's such a thing as like a shared lock, right? If I want to lock all 3 things at once, there should be a way to say I want to lock A and B, right? Here's the problem, right? If we have one resource in that category, how many, we only have one shared lock, right? If we have 2, we have A, B, and AB. So we have 3,
Oh, it starts getting okay.
right?
Fix it.
If we have 3, we have A, B, C, AB, BC, AC, and ABC,
And as far as I'm concerned.
right? So you've got 7, and we're only at 3, right? You can see that this is exponential growth,
Yeah.
right? Yeah, so that's the problem with that, right? Sure, with our,
It works with our 2 users, but not at scale.
yeah, exactly. Like for any in-class example that we do, that would probably suffice. But yeah, if you're doing things at the level of an operating system, right? Like,
4 billion locks.
yeah, like basically the number of locks in that scenario grows quite strongly exponentially on the number of things you're trying to lock, which is ultimately like infeasible, unfortunately. Although it's not a bad solution if it weren't for that, right? A graph. So this is how it works. Yeah. I lock. I have all my locks. Only once I have all my locks, I do my operations, then release. Two-phase protocol. A growing phase and a shrinking phase. I would say, because, I'm a pedantic kind of guy, the two-phase protocol is actually a 3-phase protocol, because you have a growing phase, a shrinking phase, and the phase where you actually execute the stupid thing. So that's 3 phases, not 2. Stupid. Yeah. But, I guess the operation itself is considered to not count. Anyway. So, here are the rules of 2-phase lock protocol. If you violate these rules, then you're violating the protocol. Number 1, 2 transactions cannot have conflicting locks. So 2 things cannot lock the same thing at the same time. Obviously, no unlock operation can precede a lock operation in the same transaction. So we must do all of our locks before we do any unlocking, right? All of the required locks. No data are affected until all locks have been obtained. We do not begin operation until we have access to all of the required resources. Make sense? So far so good? Like, this course could be pretty good if it included, like, in the slides, explanation of what deadlock actually is, Too little time, so many courses to fix. Lock modes. Shared lock. One user asks to read a record. The other user may read it, but no user can update it. So when you open a file in read mode, you are opening it with a lock of a form, but it doesn't prevent other people from reading it, right? That's the thing about reading versus writing. Reading is a non-destructive process, writing is a destructive process. The thing should be locked from writing while it's being read from, right? Because otherwise, if you're reading through a file and something writes into it halfway through you being finished writing to it, you end up with inconsistent memory. And you don't want to end up with inconsistent memory. But as many people as you want can read from it at a time, right? Because it's non-destructive, right? An update lock is a temporary state before an exclusive lock. It's like, I want to update this. All you people clear out. I'm going to change it. Exclusive lock. One user asks to modify a record. No other user can read or modify it until I'm finished. So, question. Which SQL statement will result in a shared lock? Select. That's right, because that is our read operation. Why bother locking a record before it's being read? I think I kind of actually already explained this. It's because you don't want it updated mid-read, right? Why is an exclusive lock necessary? Why prevent users from reading a record? They may read it inconsistently while it's being updated. Okay?
Oh, thanks.
Yes. I like my explanation better though. The deadly embrace.
It sounds like a romance novel.
I mean, yeah, and like not a good one either, like.
Or it's so bad it's good.
Yeah, like you would expect to find this one in like the second shelf of 3 bookcases full of Harlequin romance, The deadly embrace. Yeah. Sophie, a poor farm girl in the American Midwest, goes to school and meets, Roger Burt McChin, the most handsome man who's ever lived, but he has a dark past, Yes. Little did she know that he was planning the murder of his ex-wife, who deserved it. Anyway. So yes, a deadlock occurs when T1 obtains a lock on X, T2 obtains a lock on Y, T1 requests the lock, T2 requests the lock for the other one, neither one can give up the lock until it's got the other one. Have you guys ever heard of the dining philosopher's problem? It's a related problem to this. Okay, this is the dining philosophers, all right? Let's imagine that you have a table, all right, around which there are 5 philosophers. Each one has a plate, and there is a pile of food in the middle of the table, all right? Now let's imagine that each philosopher has around the table between each plate is 1 spoon, between each pair of plates. So it looks like this. The dining philosophers. Food. Spoon, 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 spoon. And you have the philosophers sitting around the round table, right? I can't give you the proof, but there is mathematical proof that, I have to explain the condition. In order to eat the food, each philosopher requires 2 spoons. All right? So it is a mathematically verifiable result that there is no algorithm that prevents one of the philosophers from starving to death. And That's the dining philosopher's problem. Look it up sometime and you'll get a much better explanation than I just gave you. But yeah, no, at least one of those philosophers will die in that scenario. Because I think it's like, if a philosopher grabs a spoon, they won't let it go until they've got the other spoon and then eat. Right? And then, because that's the deadlock, right? If this guy has this spoon, and this guy has this spoon, and this guy has that spoon, and this guy has that spoon, and this guy has that spoon, they all starve to death. Right? Because none of them are going to release the lock on the other spoon so that they can eat. And apparently, no matter what kind of algorithm you construct, at least a couple, like, someone eventually starves to death. But yeah, anyway. Deadlock control. Prevention, yes. Transaction is aborted and rescheduled if possibility of deadlock exists. So you might be able to predict if a deadlock is about to occur. If the deadlock is found, so basically if you put a timer on these two tasks, and if they take longer than they should to execute, you kill one of them. Make it release its lock. Say, you have to wait completely. Give it up. And so he does. Avoidance. Obtain all locks in succession before executing. This increases action response times, but reduces deadlock. Recommendations. Detection has a low probability of success. Prevention has a high probability of success. I don't know what low and high probability mean in this context. Use avoidance where response time is a low priority. Okay, so there you go. It's a problem. Deadlock is a problem. I think we're almost done, guys. 2 more slides. Database recovery management. The database, failing for unexpected reasons, occurs occasionally. Possible causes are power or hardware failure. Sometimes your computer just catches fire. It happens, right? Nothing you can do about it. Oh my gosh, did I ever tell you guys the story about my RAM chip? Alright, so I have like a desktop workstation, and like a RAM chip blew in it, and it just kind of, the chip blew, stopped working.
Was this the one where you sent it to the IT?
Yeah.
Oh.
It was like 8 gigs. By the way, we all know about RAM now, right? If you weren't in the last class, I talked about how RAM prices have gone up by like a factor of 6 or 7 in the last month because OpenAI has literally bought 1/3 of the RAM in existence. So if you want to buy a laptop, do it now because those prices are being passed down to hardware manufacturers next year. I bet you anything.
I remember a few months ago you said something about how if we could choose between like taking up CPU processing cycles and memory, we should take memory because memory is cheap. Not so much anymore, huh?
I'm very, very grateful that last year I decided to buy 64 gigs of RAM for my PC.
Yeah.
Because that is like $700 now.
Yeah.
It's not good.
Yeah. That's like more than half. You can get like that's at least half the cost of a laptop. Like. But anyway, so I had this workstation and the RAM chip blew in it, right? And I'm like, well, I mean, I could spend like $40 or 20, however much it was, and replace that with much more RAM than I had before. But, I hate myself, and I wanted to see, it was a kind of an experiment to see how bad IT actually is, because like, I'd heard stories about how IT is bad, but I needed to experience it for myself, right? So, because it's like, you can say IT is bad, but unless you've had the personal experience of it, you're kind of just repeating like other people's opinions, You should have your own well-formed opinion. So I said, okay, IT, this is your machine. Fix my RAM stick, please. Here's the burnt out one. The mistake I made was pulling my own RAM chip out. right? Now, just between you, me, and the fence posts,
And the camera?
yeah, that's mine. I had put my own hard drive in this thing so that I could use Linux, right? So that's a little trick for you. Okay, if you're ever working anywhere and they give you a workstation with an unlocked bootloader, that is your computer. You can do anything you want with it, including put a new hard drive in it. Just make sure that you are aware when they take it away so you can stick your hard drive out. So that's what I did, and it's a good thing I did too, because like, you know, most of my stuff is like backed up to GitHub, you know, but some stuff isn't, and it turns out my computer was in the shop for 22 days
Oh, wow.
for one RAM stick. This is how things worked, right? I said, here's my computer, take her away. I don't think you need to take it away. All you need to do is open up the side and put a stick of RAM in it. But sure, you want to take it back to your shop, take it back to your shop.
5 minutes at most.
Right? 5 minutes at most, yes. So they take it away, and a week goes by, and I'm like, hey guys, where's my computer? And they're like, oh, what was it exactly? The RAM slot might have become damaged. You weren't in this yourself, were you? We know you were, because you gave us the RAM separately. And I'm like, I didn't break it. You guys probably broke my computer fixing the RAM. No, I didn't damage the slot when I took the RAM out, you psychopaths. So yeah, I was like, okay, so, alright, it's got a damaged RAM slot. Where whither now, IT department? And they're like, we have to get the Dell guy in, because the motherboard needs to be replaced. And I'm like, okay, when's the Dell guy coming? Next week. Okay. Next week the Dell guy comes. He's gonna replace the motherboard. Alright. Apparently, I was talking to some guys around the office, and like, replacing the motherboard is like Dell's go-to solution for anything wrong with your computer, apparently. I didn't realize this. I think it's a bit silly over a RAM stick, but alright, so the Dell guy comes, alright? It's like, well, some of the screws holding your motherboard to the casing may have become stripped. And I'm like, stripping screws inside of a computer, that's metal shavings inside of a circuit board, you psychopath. Alright. So, the Dell guy didn't have the right screwdriver, attempted the operation anyways. So I still need a new motherboard. What's happening now? We're sending it to Toronto. Okay, alright. This whole time, I'm keeping one of these in my cubicle, right? For every day that goes by that my computer is in the shop, right? That's how I know it was 22 days that it took to sort this out. So, okay, it goes to Toronto. It comes back, and I'm like, is this even still the same computer, or did they just swap it out for a new one? I have it. It works. It has the new RAM stick. And I plug my little Linux disk in, and I'm like, oh, the operating system you gave me that I don't use, alright, I don't even care. I got my computer back. I actually, during this process, I bought like one of those, they look a little bit like a toaster, but it's like a little slot thing that you take like a spinner disc and you stick it in the top. Kind of like the Nintendo that the angry video game nerd uses. And like, that's kind of cool. You can get tools, like dual slot ones where you can like clone a drive. It's kind of cool. I only need one slot though, but. Alright. So anyway, unexpected unexpected hardware failures are unexpected, but can happen. And then you can have long periods of IT wanting your computer. I told my boss and I said, when people complain about IT, this is what they're talking about. Recovery restores the database from a given state, usually inconsistent, to a previously consistent state. Techniques used based on the atomic transaction property. I love those sentences that don't have enough of the small words in them. As each modification to the database, it goes to the transaction log first. It will be written to the database at a later time. Log records for database modification record either the logical operation performed or they record the before and after images of the modified data. The before image is a copy of the data before the operation is performed. The after, really? Before means before, after means after. It's like in that one Alien movie where they explained that a scanner scans things, you know? You know the one I'm talking about.
No,
No?
I'm thinking of one time my best friend came to visit me and we went to a consignment store and she asked, what's a consignment store? I told her it's a place where things go to get consigned and she got real mad at me.
Recursion.
Yeah, no, I think it's in like Alien Prometheus or something. One of the old, like it's old now, but like there's this guy who like has a little drone thing that he throws into a cave and it's like, yeah, we'll use the scanner. It's going to scan the environment.
Yeah, the movie where the scientists have no survival instincts.
No, this is the movie that spawned the Prometheus school of running away from things, right? Because like there's this giant donut that's chasing a character, and they're like, "Oh no, the donut's gonna crush me!" And then they just ran like laterally, they'd be fine. But instead, they chose to run in the path of the rolling donut. Anyway, in the event of a crash, the database administrator restores the database from the latest backup and then applies the transaction log. That's the whole reason you have a transaction log in the first place. One might say that the transaction log might be in the database itself. Presumably, this assumes it's being stored on a separate machine. Thank you, and good night.
The last lecture.
This is the last lecture. I've got 3 minutes remaining for like final notes, I guess, which are about the exam. Tomorrow morning, 9:30 a.m. in the room down the hall, we will be having our big fat exam review for this class. I will try to get more sleep than I had last night. Although it's not really up to me. We will probably be going through the second of those 2 big normalization case studies that occurred last week. We will review any of these topics as you feel that you want me to review them, but honestly I think that probably going through the ERD is the best use of our time. So, any questions? Yeah?
I just have a question. Is there all the resources practice again normalization cycles that are in the MyCanvas?
No.
Is there a way I can get more than those two?
Ask ChatGPT to make it for you.
I appreciate that you came to this legal class and learned about philosophy and retake that and also naval signal science.
I mean, that's why you come, right? It's the whole package. You know? The more boring the material is, the more I find my mind wandering.
Yeah.